Okay, in this one, I want to talk about put some additional gloss on the idea of equilibrium solutions. So recall last time we learned that if you have an autonomous differential equation, one that looks like x prime equals f of x, then an equilibrium solution is one which is a constant function of the form x equal to c, where c is what we call the critical value or a critical point of this differential equation. That is to say, x equals c. C is a number for which f of c is equal to 0. Okay. Reminder: if we look at these differential equations through their slope fields, for example, if we look at x prime equal to x, here is the slope field of it. You'll notice that x equal to 0 is a equilibrium solution. And the reason is because c equal to 0 is a 0 of the function f of x, in this case being x. Okay. If you go to something a little bit more sophisticated, like x prime equals 0.1x times f minus 5 minus x, then there are two equilibrium solutions. One corresponding to x equals 0, because that makes this equal to 0, but also one corresponding to x equal to 5, because that also makes this function here equal to 0. Okay? So equilibrium solutions in and of themselves are very easy to find. You just set f of x equal to 0 and solve. Now, I want you to notice something about this equilibrium solution in this first slope field here. Notice that if you're sitting at the equilibrium solution, that is to say, if your x is equal to 0, and you perturb yourself a little bit off of the equilibrium solution, maybe you're a little bit bigger or a little bit smaller, that you don't like if you then let time run. So if you then let time run from here, you're going to slide along this solution here, and you notice that as t gets larger and larger and larger, you're getting closer and closer to the equilibrium solution x equal to 0. And it doesn't matter if you perturb yourself a little bit above or a little bit below, either way, you're going to get closer and closer to x equal to 0. For that reason, we call this particular equilibrium solution a stable equilibrium. On the other hand, to contrast, look at this solution down here. This equilibrium solution, x equal to 0, for this different differential equation. If you perturb yourself a little bit off of this equilibrium, then all of a sudden you are veering quite far away from the equilibrium solution x equals 0. Similarly, if you perturb yourself a little bit below x equals 0, you're going to go, to negative infinity. Yeah? And so there's something unstable about this equilibrium. All right? Think of an analogy being, think about the difference between a rock, like a marble, sitting on top of a hill. If you perturb that marble at the top of that hill just a tiny little bit, I don't know why I'm asking you to visualize it. Say you have here's a hill, and you put a marble, you balance it so that it's at rest. Very carefully you place it so that it's not moving, it's not falling down the hill in any one direction. This would be an unstable equilibrium, because any tiny perturbation is going to make it move quite a bit away from its current position, right? It's going to be a very, very different situation for this system if we perturb this equilibrium just a little bit. Contrast that with a marble that's sitting at the bottom of a valley. If you push the marble in either direction, it doesn't matter, it will return to where it was in the long run. This would be called a stable equilibrium, right? The same kind of idea applies for solutions, equilibrium solutions to differential equations, okay? And what we want to be able to do is to distinguish stable solutions from unstable ones, okay? And we're going to do that through a tool called a phase portrait. And we'll talk about that in the next video.